Last time we talked about random experiments and counting. Today we'll kind of continue counting stuff, but we'll further define something called a probability. You guys have heard this word before. And then next class we talk about chances and odds, very much related to probability. And then we have our review, and then we have test number 2 on April 17. Any questions on that? I think that's a week from Tuesday. Okay, and also today, project number 1 is due. So I've already gotten about half of them before, which is super. But if I don't have yours yet, hopefully it's in the folder. If it's not in the folder yet, you'll want to give it to me as soon as possible because the penalties are 5 points a day for every school day that I don't have it, okay? So if it's not done yet, but you get it done tonight or tomorrow, email it, and then the penalties stop. So as soon as you can, get that to me. And we'll start here on page 33, number 1. First, were there any questions on that how many activity from last class? The first question, which I think most of the groups got all the way through, was about counting license plates. Any questions about the license plates stuff? Okay, and hopefully we had a chance to continue on, even if it was outside of class. Any questions about whether we're using P's or C's for any of these questions here? Yes, Becca. It is, but to be honest, I'm never going to ask you to use the formula, but this is what you're asking about here? Yeah, so Becca says, are those parentheses necessary? Yes, they are. Okay, so no questions about any of this stuff? We're feeling okay about whether we choose P or C or multiplication rule? Okay, then let's move on to number 2 on page 33 with we now. We'll go to Zach. Okay, Henry. Okay, so here we're going to ask you guys if you know a little bit about a deck of playing cards. I'm assuming that at least one person at every table knows enough to answer these questions. So can you guys tell me how many different outcomes there are in each event? For example, how many different ways is there for a card to be an ace in the standard deck? How many cards are aces in the deck? There are 4. And some people are already headed to probability where they say 4 out of 52. Right now we're just counting how many aces. So can you guys do the other 3 with your neighbors, especially if you don't know much about cards? How many cards are there that are spades? There are 13 of those. How many cards are there that are the 2 of spades? Just a single one. And how many cards are there that are red spades? 0. All of the spades are black. I think we did. Yeah, because the but if you're counting 10 regular cards, then I think you're already counting the ace as the 1. Yeah. Yeah, 13. Okay, so on the test, I'm not going to ask you like questions about cards without giving you some important facts. So I don't need you guys to all be card sharks on the test, but I figure here there's at least one at every table. We'll go on to 4 with Holly. Oh, hold on one second. Justin? Yeah, so Alex wanted to know if we were counting the ace or not. And so there's a bunch of numbers in the deck. There's 2, 3, 4, all the way up to the 10 of spades. And then there's the picture cards, the jack, the queen, and the king. So these are also called the face cards. And then there's an ace, which you could either put at the top as a high card or at the bottom as a low card. I like to throw it down there because then it looks like a 1 through 10. So altogether there's 13. And I think these guys were counting the ace as a 1, but then not realizing they had already counted it and wanted to count it again up here. So it's there are 4 aces in the deck, and there are 13 spades in the deck. Yeah, you're welcome. Okay, Holly, number 4. Okay, so we know 0.1 as a percentage is 10%, right? 0.1 equals 10%. And so if the weatherman says that there's a 10% chance of rain today, it means that if there were a whole bunch of days just like today, then on 10% of those days, we'd get some rain. On the other 90%, no rain, okay? Now, obviously, there aren't a million days like today. There's only one. And so we can't say with any certainty whether or not there's going to be rain on this specific day. But if we were able to run it over and over again, which they do with computer simulations, they figure about 10% of the days, just like today, we get rain. So that's what it means when the weatherman says 10% chance of rain. Okay, let's go down to this next line here. Probabilities range from a certain number. What's the probability of an event that's impossible? 0. If something never happens, there is a 0% chance of it happening. How about an event that's certain to happen? Is 1, or if you like percentages, 100%. So probability is always between 0 and 1. And then finally down here, some notation. We'll go to Jocelyn. Last line. Okay, so if you see PR, it stands for probability, and then inside of those parentheses will be a specific event, like on this next page. Alex? Okay, so the first part we'll do together, and then you guys will do the other 3. That PR, again, stands for probability. So if you pick a single card from the deck, I want to know what's the probability that the card is a diamond. So I think a lot of us already kind of feel this is going to be a fraction. Probabilities are fractions. How many successes, how many diamonds are there in the deck? There are 13 diamonds. And divided by how many cards are there with no restrictions? There are 52. So you have 13 chances out of 52 to pick a diamond. Generally, we reduce stuff, but 13 out of 52 is fine. Questions on that? Okay, so I'm going to ask you guys to do parts B, C, and D, again with your neighbors. We haven't even defined what probability is. All we've done is written a fraction, but I think a lot of us already feel why that's the right fraction. So check with your neighbors and do B, C, and D. What did we get for the probability that the card is a heart? Is also 13 out of 52. 13 hearts, 13 things that we are calling a success, divided by 52 cards. And so we've got our basic definition for probability just off the screen here, but it always involves the number of ways that you can actually accomplish whatever is in the parentheses, the number of ways we can actually pick a heart, 13 of them, divided by the total number of ways to do anything. It's always how probabilities work. On the bottom, you put the total number of ways you can do anything with no restrictions. In this case, you're just picking a card from the deck. There are 52 ways for you to do that, 52 choices. How about the probability that the card is black? 26 out of 52. There are 26 black cards in the deck and 52 total. One reason that I don't like to reduce all the time, if you reduce here, that's a quarter. If you reduce here, that's a half. Some of you guys just put half the deck is black. But then when we come down to D, it says find the sum. Is it easier to add the sum in the reduced column or the original column? Original, right? Because you need a common denominator to add them up. Either way, what do you get when you add them all up? You get 52 out of 52, which is also 1. You get 1. Why do we get 1? Right. Every card is in there somewhere, right? Every single card is in there. So if I said, pick a card from the deck, what's the probability that the card is a diamond or a heart or black? 1. I've described every single card in the deck. You're going to pick one of them. Okay, how about number 6? Blake, you get this hard word here. Equiprobable. Okay, so assuming we have a regular deck of cards, would you guys agree that every card in the deck is equally likely to be picked if I just said pick a card? There's no favoritism, there's no leaning towards one kind of card or another. They're all equally likely, equally probable, hence the funny word there. If you roll a die and it's a fair die, then every single outcome is equally likely, right? You're going to get a 1 just as often as you get a 3, as often as you get a 6, all equally probable. And so everything that we do is going to be in an equiprobable space. And then we can apply our definition here in number 7. We'll go to Zach. Okay, so that right there is exactly what you guys did up above. You didn't need a fancy formula for it. But if we wanted the probability that the card is black, you found the number of outcomes in the event, the number of cards that were black. That's the event. Divided by the number of outcomes in the sample space, that's everything. The total number of cards was 52, 26 out of 52. All right, more stuff with cards. Can you guys again pick a card from the deck and find the probability of every one of these things in question 8? Go ahead. So it seems like groups were making real good progress on these. The one I want to talk about is the last one. I've got the answers up for the others. The last one I think is the tricky one. We want the probability that the card is black or a king. How many cards are there in the deck that are black? 26. Black cards, there are 26. How many cards are there that are kings? There are 4 cards which are kings, and it sure feels like we should add them up and get 30 out of 52. What's the problem with just adding the black cards to the kings and saying there's 30 out of 52 ways? Yeah, we've got some overcounting here. And overcounting is really dangerous, and it's sometimes easy to miss. I think a lot of us caught it here. But inside of that 26 is some of the numbers that is inside of that 4. There are 2 cards that are in both categories. Which 2 cards are in both of these things? There's the king of spades and also the king of clubs. Both of those cards are black, so they're part of the 26. Both of those cards are kings, so they're part of the 4. So we need to make sure we don't count them both again. And so the right answer here is actually not 30, but 28 out of 52. It's getting rid of the overcounting by 2 that we did before. Questions on that one? Okay, let's try number 9, and we'll go to Hillary. Okay, so this one is tougher. We're taking 2 cards out of the deck. First, let's see if we can figure out what goes in the bottom. What I'd like to do is write down in English what I'm trying to count, and then we'll actually put some numbers where we count it. But in the bottom is supposed to go the total number of ways to do anything. How many cards are we picking here? We're picking 2 cards, so we want the total number of ways to pick any 2 cards. So let's see if we can find that number before we worry about what goes upstairs. Total number of ways to pick any 2 cards. So you're picking 2 cards. The first question that we have to ask, this is now going back to what we talked about last class, is are you allowed to repeat? Like on a true-false test, you can put true more than once. Are you allowed to repeat the same card more than once? No, you're picking 2 cards from the deck. You're not picking 1 card and then putting it back and then maybe picking it again. Okay, so we are not allowed to repeat. Repetition allowed. The answer is no. And so the next question has to do with order. Does the order in which I pick these cards matter? The answer is no. Don't have to know anything about cards. It says the order doesn't matter. And those 2 answers right there tell us to use combinations. Okay, so let's try combinations. The first number is how many things you have to choose from. 52, you can choose any cards. The second number is how many you're actually choosing. You are choosing 2 of them, 2 cards out of the deck. And maybe somebody with a calculator can punch that number in for us. And so there are 1,326 ways to pick any 2 cards from the deck. So, for example, you could pick these 2 cards right here. What if I switch the order? Is that the same or different? That's the same. So you could pick these 2 cards. Or I'm going to keep showing you the same 9 of diamonds. You could pick these 2 cards. That's a second way. Or you could pick these 2 cards. That's a third way. Eventually, I'm going to run out of all the ways to pick the 9 of diamonds and another card, right? I'll throw that one away. I'll bring these guys back. And then I'll show you all the ones that involve the 7 of clubs. So it could be these 2 cards. Whoops. Or it could be these 2 cards. Or it could be these 2 cards. If I keep doing this, this would take a lot longer than we have today. How many different ways would we be able to grab pairs of cards? 1,326. That's what that is. And you can see the power because I don't want to sit here counting all of these things. But if you just answer a few questions and then use the tool, combinations, then you get your answer. Do we like my oversized deck of cards? Isn't that nice? Just for comparison purposes, I'll show you. It's a standard, there's a standard card right there. I think actually you can fit 4 of them. Okay, so that's 1,326. Now we go upstairs. Again, we're trying to find the probability that both cards are red. Both cards are red. So then in English, we've got to figure out what we're counting before we try to count it. Number of ways to do something. What are we trying to do? Pick red cards. Number of ways to pick how many? 2. Red cards. Yes? Number of ways to pick 2 red cards. Could be 7 of hearts, 6 of diamonds, Jack of diamonds, Queen of hearts. There's lots of them. There's not as many as we had before, but there's still a lot. Let's ask our 2 questions. Is repetition allowed? You're going to pick the same card twice? Still no. Does the order matter? Still no. What do we use? Still combinations. Here's the tricky part, is finding out what we put in this new thing. I'll put the second number first because that's easier. How many cards are you picking? Still 2. Can you guys talk to your neighbors about what to put first? How many choices do we have? We have 26 choices. What you are doing is restricting the deck of cards. You're throwing all the black cards away, and you're saying, I'm just going to look at this smaller deck of cards, which has only reds. And then I'll let you pick any 2 that you want. And as long as I only allow you to pick from this red deck, you're going to pick 2 red cards, right? So how many cards do you have to choose from upstairs? 26. If I'm forcing you to pick red cards, you have only 26 choices. You don't have 52 anymore. Do we buy that? Okay, what is 26C2 from the calculator? 325. So this is our fraction. If you want a probability, we can type that in and get a decimal. Somebody have a number for me? 0.245. So that's about 24.5%. Sure. But this one is less than 25%. That's strange. Less than, I mean, it feels like it's so close to 25%. Why wasn't it 25%? Let's think about the possibilities for picking cards. You could have both red, you could have both black, or one of each, one red and one black.
Yeah, but it's going to change once you pick, say, the first red card.
Let's come back to, I want to come back to that argument. I'm not even ready for it yet. First, I want to recognize I have only 3 possibilities. Doesn't it seem like if there's only 3 possibilities, then there's like a 1 in 3 chance of getting reds? We buy that? I have only 3 possibilities. It's either red, red, black, black, or one of each. And if it's 3 possibilities and it seems like they're all equally likely, it feels like it should be a 1 out of 3 chance, which would be 33%, which is not this. First of all, why are we close to 25%, 1 out of 4, instead of 33%, 1 out of 3? We are picking 2.
So roughly, if you pick the first, if you just pick one card out of the deck and having that one red, you have 50-50 shot.
Mhm.
But for the second time.
Can you pause? I think you're going to give me the same argument that I'm not ready for yet, but we need this argument, but we don't need it yet. We need a different argument right now.
Changes. Because now you're dealing, depending on, if your first card is black,
Hmm?
at that point, now you have 51 cards in the deck, but it's 26 red and 25 black. So now you actually have a slightly better than 50% chance for your next card.
Okay, so this is why it's slightly different from 25%. But I'm still not clear on why it's not close to 33%. I'm kind of pulling the wool over your eyes right now. I'm telling you there's 3 outcomes. Red, red, black, black, one of each, right? To say that there's a 33% chance assumes that all of these outcomes are equally likely, and they're actually not. Do you know that one of these is a whole lot more likely than the other 2? Getting 1 card of each. Yeah, getting 1 red and 1 black is a whole lot more likely. I said that the order doesn't matter, but let's pretend for a second that it does. Suppose that I show you the 10 of diamonds, and I'm going to pick another card in a second. The choices are red, red, black, black, or one of each. This is the first card. It's the 10 of diamonds. What could it still be when I pick the second card? Could it be red, red? Yes. Could it be black, black? Not anymore. Not if this is the first card that I've already picked. Could it be one of each? Yes. Okay, so right here, I've still got a couple of things in play. If I pick a red card, I still have red, red, and one of each in play. What if the 7 of clubs is my first card? Could it still be red, red? No, it takes red, red off the table. Could it still be black, black? Yeah. Could it be one of each? Yeah. But regardless of which one I pick, either red, red, or black, black is getting taken off the table. But what's still in play no matter what the first card is? It's still the one of each. So automatically one of them is tossed. If you pull out a red first, you're definitely not black, black, but you could still be one of each. So those 3 outcomes are not at all equally likely. It's really, really close to a quarter of the time is red, red, a quarter of the time is black, black, half of the time is one of each.
So if you pulled your first card and put it back in the deck and pulled the second card, would it increase your chances to an even 25%?
Then it would be perfectly 25%, 25%, 50%. And now we get around to this argument about why is it not exactly 25%. It's because if you pull out that 10 of diamonds, that red card is now out of the deck. You still have 26 red cards available to you for the next one. You have only 25. Doesn't change a whole heck of a lot, but it changes a tiny bit. Went down from 25% to 24.5. Okay. All right, so that is the answer to the question. If you pick 2 cards and you want to know the probability that they're both going to be red, about 24.5%. Questions on this? Okay. raise your hand if you've heard of the game show Let's Make a Deal. Almost all of us. So this is a game show that was on many decades ago. I think it's gotten reborn and it's maybe, is it currently on still?
Yeah, I watched it.
Awesome. Who's the host? Who's the host? I feel like it was Wayne Brady for a little while, but I don't, yeah? Yeah. But the old version of this game show from back in maybe the 70s, it was Monty Hall. Do you guys, any of you remember like Monty Hall running Let's Make a Deal? And so you'd have all these people dressed up like it was Halloween, but it wouldn't be Halloween. They would just dress up and they'd wear these ridiculous costumes and they would hope they get picked by the host, and then the host would offer them some silly opportunity to make some money or get embarrassed. Either way, they would get embarrassed usually. But we're going to look at this thing called the Monty Hall problem. So we'll begin here with this description, and I think we are up to Kelly. The Monty Hall problem. Okay, we'll go Brittany. Do not want it. All right, I don't want to force you to read. Go ahead. Okay, so let's actually look at an example of this. So there's this website which you can take a look at the link for. So here are my 3 doors. Behind one of these doors is a car, something quite valuable, and behind the other 2 are pigs. And obviously we'd like a car, I think. So we're going to pick a door, 1, 2, or 3. Phil, 1, 2, or 3. Okay, Phil has picked 3. Now, what we could do is just open door number 3, and Phil has either won the car or a pig. And I'm pretty sure they force you to take the pig home when you win the pig. So we could just give him door number 3, but we're going to make it interesting. We're going to say, okay, I'm not going to show you what's behind door number 3 just yet. I'm going to show you what's behind one of these other 2 doors. I'm not going to show you the car. I'm going to make sure I show you the pig. Do you guys agree that definitely behind doors 1 or 2, there's at least one pig behind one of these doors, right? They're not both cars. So regardless of whether Phil has gotten lucky with the car behind door number 3 or a pig behind door number 3, one of these doors over here has a pig behind it. And I'm going to show you a door with a pig. So you pick that door. Okay, there's a pig. And now we're going to give him the choice. What's the choice we're going to give him? Do you want to stay with your door number 3 or do you want to switch to door number 2? Okay, so you can pick. What would you like to do? Okay, so staying with door number 3 was a bad choice. The car was behind door number 2. Okay, so here's the question. We'll play one more time. Maggie, 1, 2, or 3? 2. So there's a pig behind 1. Stay with 2, switch to 3. Okay, we'll stay with 2. That was a good choice. So you can drive your pig home, maybe. So here's the question. Should you always stay with your original choice? Should you always switch to the other choice? Or it doesn't really matter in the long run whether you stay or switch? Can you guys talk to your neighbors? And in 30 seconds, we're going to make our best guess. All right, so the questions again are, is it better for you to always stay with your original choice? Is it better for you to always switch when given the opportunity? Or does it not really matter in the long run? It's kind of 50-50 either way. Raise your hand if you think it's better to stay with your original choice. Okay. Raise your hand if you think it's better to switch when given the opportunity. Raise your hand if you think it doesn't much matter. It's 50-50. Okay, and that's the vast majority of you guys thinking it's 50-50. So what you're going to do is you're going to collect some data. You guys are going to play this game right now a whole bunch of times. You're going to partner up. I have given each of you guys, each pair of you, a set of 3 cards. One of them is a picture card. This one right here. Everybody knows what a picture card looks like? Has a face on it. The other 2 are not picture cards. The picture card is the car. The other 2 cards are the pigs, okay? You guys are going to run this game. I will just do one demonstration here so we mix them all up. And we will say, Becca, 1, 2, or 3. Becca says 1. I need to do some thinking as the host. I cannot show her a car, right? I need to make sure that when I show her something, I don't show her a car. So I'm looking at these, making sure I don't show a car. I'm also not going to show her what she picked. I'm going to say, Becca, this one is a pig. Would you like to stay with 1 or switch to 2? So she stays with 1. She lost. If she had switched, she would have won the car. And all we're going to do is record that data. She decided to stay. You don't need to record it now. She decided to stay, and she lost. And there's on the piece of paper down at the bottom, there's a collection of things. And if Becca and I were playing this game for real, I would put a little hash mark right here and said she stayed and she lost. And if she stayed and lost, then we put, and you just keep tallies. Okay? So you're going to run, let's say 15 of these things in one direction and then switch roles. Okay? Record all the data.
How many you said?
15. 15 and then switch roles. 15 rounds. So here's our data. It's a lot of raw numbers. It's hard to analyze in this current form. How about we think about percentages instead? Let's just look at the first row. When we stayed, we won 71 times and we lost 113 times. Let's find out how many we played total. How many games did we play total? Oops. Okay, so if we stay, then the probability that we win, if we stay, the probability that we win is how many out of how many? 71 out of 184. Agree? We won 71 times out of the total number of times 184. Somebody get me a percentage here. Anybody have a number? 71 over 184? 38? Okay, so we'll say about 38% of the time. If we switch, what's the probability that we win? Something out of something. Is it still 184 for that one? We have to only look at the games where we switched. It's only the bottom row now. 131. Can somebody get me a percentage there? 76 out of 131. 58. Jocelyn? Jocelyn, did you have your hand up? Okay, thank you. All right. So when we stayed, we won 38% of the time. When we switched, we won 58% of the time. First of all, it seems weird. Should they add up to 100? They don't. Should they? No, these were two different experiments. You stayed, and that was one experiment.
When you stay, when you pick that one card, when you stay, you have a chance. 3%. But when you switch, you get a shot with that card.
Okay. Okay, so that 58 is close to 50. 38 is close to 33. I don't think they need to add up to 100% because there were two different experiments we ran. But I do know that most of you guys said, should you always stay, should you always switch, or it doesn't matter. Most of you guys said it doesn't matter, meaning it's like a 50% chance whether you stay or switch. If you stay, you won a lot less than 50% of the time. If you switched, you won a lot more than 50% of the time. This leads us to believe that it is not a 50-50. It also leads us to believe that switching is the best strategy. Now I want to try to convince you guys that it is the best strategy. So first of all, it's really counterintuitive because it feels so 50-50. The moment that we open that door, let's go back to our pig example here, this guy. The moment we open the door, it feels like it's gone to 50-50. So let's give this a shot. All right, so we'll go to Wadada. 1, 2, or 3? 2. Okay. It feels 50-50 at this moment because you can either stay with 2 or switch to 1. Door 3 is out of the picture. You have a 1 in 2 chance of winning. It's simply not true, and the data suggests to us that it's not true. So here's what's going on. If you stay with 2, And I'd never bother revealing door number 3. If you just decide you're going to stay with door number 2, what's your probability of winning? Is 33%. You have a 1 in 3 chance of winning. If you pick door 2 and you stay with door 2, it's 33%. You could decide before I even show you the pig that you're going to stay. The fact that I've shown you the pig didn't affect you. And if you don't switch, you're not acting on the information, and nothing has changed. And I think this is what Charlie was getting at. You have a 1 in 3 shot. If you stay, you have a 1 in 3 shot. That's it. It doesn't matter that I show you a pig. I could always show you a pig, regardless of whether you picked the right thing or not. So the 38% that you guys got when you stayed was actually pretty good, because it should have been only about 33%. So we got kind of lucky, just there's chance variability, chance error. It should have been 33%, and if we kept playing longer, it would come down to 33%. So let's think about what happens when we switch. In this picture, if we switch, we move to door number 1. It feels like there's a 50-50, right? Because 1 is a pig and 1 is the car. Turns out it's not 50-50. I'll try to convince you in 2 different ways that it's not 50-50 if you switch. First way, if you stay, what's the probability that you win? It's 33%. You have not acted on the information. Nothing has changed. There's no 50%. You could decide to stay before we even show you the pig. If you stay, it's 33%. Well, if staying makes you, if the chances of winning when you stay is 33%, then the chances of winning if you switch must be the other 66%. If you stay and you win, that's a 33% chance. Well, it must be that the switching is the rest of the chance. It's 100% total. You're going to win if you stay or switch. You have to win by doing one of those 2 things. One of them is the good. It does absorb the probability. And let's think about this way of explaining it. Suppose that I'll just switch over here and see what happens. Okay, so switching 1. Let's just take a look at these unopened doors. Okay, let's go to Zach. 1, 2, or 3? 3. Zach has picked 3. I'm not going to touch 3. Zach has picked 3. One of these first 2 doors is about to be opened and reveal a pig, right? If Zach stays with 3, then he's got his 1 in 3 chance. Nothing has happened. But if Zach switches, Zach has actually chosen more than just the 1 door. Suppose that there's a pig behind door number 1. If he switches, he gets door number 2, right? Suppose instead I showed you a pig behind door 2. If he switches, he grabs door number 1. Either way, he's basically getting what's behind both doors. He is going to grab whatever is behind doors 1 and 2. If there's a car in there, he's going to find it. Do we buy that? If there's a car behind either 1 or 2, switching is going to land on the car. If he picked the car first, if he picks the car first, it's door number 3, that's where the car is. If he stays, he's going to win. And if he switches, he'll switch off the car. That's unfortunate. Suppose that he didn't pick the car. He's picked door number 3. It's not the car. Wherever the car is behind door 1 and 2, if he switches, he's going to land on it. You buy that?
Yeah, no, actually, I get that. That makes sense. Because you're going to because you have a 66% chance that you're going to pick a pig right off the bat.
Agree?
So the chances are much higher to pick a pig.
Yes.
So then at that point, they're going to show you a pig afterwards. They're going to show you one of the losers. So yeah, by switching, that increases your chances.
It does. I'm giving you the opportunity. You can stay with door 3, or you can take both 1 and 2. What would you prefer? You take both 1 and 2, right? If you have a choice between either staying with your original door or taking the other 2, you take the other 2. You have a 2 out of 3 chance if you take the other 2. All right. One last way I'll try to convince you this is true. Suppose that we just run a few different rows here, 1, 2, and 3. And I'm going to symbolize the car with some money. So here are the possibilities. Either the car is behind door 1, or behind door 2, or behind door 3. That's all 3 possibilities. Just to make things simpler, suppose that every single time in this game, we're going to pick door 2. Every time you play, you're going to pick door 2. Switch and stay are your 2 choices. If we are in that first row, what door are we picking every time? We're picking 2 every time. Let's come back here. So we have picked door number 2. If you stay with door number 2, what happens? You lose. You found nothing. You wanted the car. So if you stay with door 2, you have lost. What door do I have to reveal to you in this first row if you pick door 2? I have to show you the pig behind 3. So you're not going to take that one. And if you decide to switch away from this one, where do you get forced to? You get forced to 1, which is the car. Okay, so in that case, switching is the right thing to do. But that was only because the money was in 1 and you picked 2. I want to do every possibility. Let's go second row. The money is now in 2. Every time we're going to pick 2. In this case, what should you do with full knowledge? You should stay. Because if you stay, you're going to win. You picked the right thing. So suppose, in this case, which door would I show you? I could actually show you either one. There's pigs behind either. So if I show you this one and you switch over to the other door, you've made a bad choice. You've switched away. So in that case, switching loses. Feels like it's a 50-50. But we have one more, and that's going to break the tie. In the last row, if we stay where we are, again, picking door 2, have we won or lost? We have lost. You found nothing behind door 2 by staying there. But if you're going to switch, what am I going to reveal to you? I reveal door 1. You are switching away from nothing. And where are you getting forced to? Money. So in that case, switching wins. We played 3 different games. If you switch, how many times did you win? You switch. You won twice out of 3. If you play this game and you switch every single time, you will win 2 out of 3 times. Alex. It's true, but I feel like I've fairly represented all the distribution. Like the car is either behind 1, 2, or 3, and I've put them all there once. If you start putting it behind 2 every time, then you're kind of forcing us to be unlucky. I feel like this is fair. It represents everything, yeah, evenly. Yeah, this is a really, really counterintuitive thing. Really, really counterintuitive. If you go look up the Monty Hall problem, you'll find lots of good information online. You can read about it some more. But it's really hard to grasp this idea that it's not 50-50. It feels so 50-50 the moment you reveal one of those doors. Okay, what I would like you guys to do is jump back. Can you guys jump back to page 30? And I think probably a lot of us have not had a chance to do number 2, so start on number 2 and see how far you can get in your groups. Page 30.